All right. Mark that last one like if you were guessing on the last question on the test before I ripped it out of your hands. And pull out something colorful to read. It's not something colorful to write with. A couple of this, okay. I got a red pen. Sorry, that was supposed to be first. Megan, short there. I think this is yours. I'm not sure. I have a problem. I have a lot of pens. Green? Nope, that's not green. Hold on, not green. Green highlighter. Okay, nope, it's gonna bleed through. Hold on. Well, I'm gonna throw you two, but not at the same time. Okay. Sharpie. And then other pen that I'm not sure if it works, but okay. Okay, so before we start grading, okay, I have a couple folks. Can you just go through some? Can you guys do your multi-step first real fast? You too? Yeah, just gonna take a quick break, mental break. And then remember, snaps, claps, smiles, like encourage them because they didn't get to see us. So, well, not before, guys, they haven't done anything yet. Okay. To make sure that they, we appreciate them. So thank you, Taz, for bringing in snacks yesterday. I made you ate. So Taz, let me go first.
I've read information on the board.
Okay, you can have this board over here. All right, let's make this snappy, guys. And then Jane's going to show us hers and then work with her stuff tomorrow. Okay. That's what you're writing.
Yeah, it's 2 boron trioxide plus 7 carbon yields 1 boron carbonate plus 6 carbon monoxide.
Awesome. Okay.
Okay, 2 moles of boron trioxide walked into a bar that happened to be approximately 3,273 Kelvin. As they were walking over to the bartender, 1 mole of carbon bumped into 1 mole of boron trioxide. The mole of carbon said, "Watch where you're going, you dumbhead." The 2 moles of boron trioxide were furious at the mole of carbon for his foul language, so they decided to beat him up. As the mole of carbon was getting his butt kicked, 6 of his carbon friends stumbled upon the fight. "Get those 2 moles of boron trioxide and make them pay," yelled one of the carbon friends. So 7 moles of carbon dogpiled the 2 moles of boron trioxide. The bartender, who was just chilling in the back enjoying the fight, reluctantly called the police. 2 minutes later, the police arrived on the scene. The fight had just finished. Carbon monoxide gas escaped the bar, so the reaction took place. The carbon monoxide gas escaped. Okay, on the floor, 1 mole of boron carbide was throwing up. The bartender explained how 2 moles of boron trioxide were fighting with 7 moles of carbon, but this random mole of boron carbide just appeared out of nowhere. The cops laughed at the bartender. "Don't you know that when 2 moles of boron trioxide are reduced with 7 moles of carbon, temperatures exceeding 3,000 Kelvin, react to form 1 mole of boron carbide and 6 moles of carbon monoxide?" They asked while picking up the mole of boron carbide and shoving him in the back of their police car. The end.
Woo! Here's good. You must get real dark with your storytelling. Thanks, sir. Put that in my box. And I don't think you can follow that, Christian. I don't think you can follow that. I'm leaving this lovely equation. Thank you, Taz, on the board. Bourbon. Boron carbide. That's what Taz is. Okay, gotcha. Right. And Christian, you can stay in the front, or if you need the board, whatever. Thermite? Right. Well, hold on. You gotta twirl. Show your shirt. How do you gonna twirl?
Oh, mine's just.
Taz, twirl for us when you get to your shirt. Stand up and twirl. Stand up and twirl. You stand there. Awesome. Okay. Thank you, sir. Okay, and twirl.
Mine's just the front side. So I
Okay.
got an explosion over here, and then got thermite written down the side, and I have a welding mask because it's used in like welding railroads together.
Got you. Thank you.
All right, so this is gonna be pretty bad, just so you know, forewarning. All right, thermite. I'm surely gonna cause some fright. Fe03 plus Al. Everything I've touched has failed. L. You're lucky I'm not found in nature. Just check out this nomenclature. My reaction is single replacement, but it's sure to cause some statue displacement. I'm too hot for you to even stop or cruising down your front lawn like molten lava. Even with 1 mole, you better run and find a hole. Don't put me on your car or it's gonna burn like a shooting star. Now to stop me, you might have to use a sandbar. that brings. Oh wait, yeah. That brings an end to this heat. I'm gonna go ahead and take a seat.
Alright, has anybody ever seen thermite, like, on TV or live? Okay, where have we seen it?
I've seen it in just like things like rolling mills and stuff,
Mm-hmm. Anybody else?
and burning holes and stuff.
Burning holes with it? Does anybody watch Breaking Bad? No? Oh my god. That's like so like 4 years ago, I know, okay. Well, they use it. And then, you guys know Justin Snyder? Okay? He made it, and we did like a demo like 2 years ago in AP Chem after exams. Everybody has to make up their own demo. He was like, I want to make thermite. I was like, I'm a little scared. Like, now knows how little hesitant I am with fire and like hair and then no hair. So we made thermite. We did it out in the big field over here. We had like clay pots to kind of make sure that we were safe, and then we lit it on fire. But the hardest thing is to light the dang thing on fire. You can't light it on fire. As flammable as it is, you can't light it on fire. So we had to light magnesium ribbon on fire, which makes like a really hot flame, and so it ignited it. And then it was a little wet outside, so he like jumped back to jump away from it, and he slipped and busted his butt. He said on camera, "Oh crap." Not that word, but I was like, Justin, and like pulled him to the side, and it's like flaming like this. I was like, this is why we don't do thermite in class. So anyway, it's most memorable demo like anybody's ever done in AP Chem, so it was great. Okay, so let me go back here for a second. We're gonna check multiple choice, so just check yes or no, and then we'll go through the mental math side of things. That's not it. That's also not it. That's it. Okay, so here we go. 1A, 2E, 3B, 4C, 5C, 6A, 7C, 8B, 9A, 10A, 11D, 12D, 13C, 14C, 15C, 16B. All right, just score yourself first out of 16, so your percentages, and then we'll go back and check some specifics. All right, so let's talk about each one kind of quickly as we go through, okay? So in one, really no, okay, well, kind of math. What did you have to do in number one? What did you do with the carbon dioxide and the... Immediately convert them both to moles, right? So you need to annotate for yourself for the quick part of the mental math, or how you can quickly approach a problem without doing all the math, like to the depth of, you know, the true values. So number one, if you convert them both to moles, what are both of them in moles? 0.5 moles, right? So 14 over 20 is 0.5, and then 22 over 44 is 0.5. So if they have the same number of moles, and then they have the same temperature and pressure, therefore, according to whose law, it's going to have the same volume? Avogadro's law, good. 2, what law did you have to use here? P over, you guys write down your math? P over T is equal to P over T, right? So you have two conditions, 1 and 2, 2. So this is Gay-Lussac's law, but it's still, you know that pressure and temperature are directly related. This is how those equations always look. You had to do what with your temperatures? Convert them both to Kelvin, right? I need you guys to respond to me, okay? So then in terms of what are you solving for here? Pressure 2, right? So pressure 2 is equal to what rearranged? P1 times T2 over T1. Well, pressure 1 was 2.5 atmospheres. And if you can get away with just putting the numbers, not the units, I get on multiple choice, you gotta be fast. What's your temperature 2? 27 degrees Celsius, which is 300 Kelvin, okay? And then what's your temperature 1? It was 127, which is 400 Kelvin. And that should be now 75% of 2.5. The only answer that even was close to that was what? 1.88, right? So this is basically 0.75, is 3 over 4 is 75% times 2.5. You can guesstimate there, it's going to be about 1.8. All right, number 3, maybe it was a little bit more challenging, but here's how I attempt anything with the R constant. What equation came to mind for this one? Molar mass equation. Molar mass is equal to what? Dirt over P, right? So you plugged in 1.3 grams per liters, 0.0821 atmosphere liters per mole K, 273 Kelvin, and 1 atmosphere, right? Okay, so this gets rough, but the way I approach it is 0.08 is approximately 0.1. Let's just call that. Okay, it's approximately 0.1. I know that when I estimate with 0.1, I can do anything. I'm basically multiplying by 10%. So what's 0.1 times 273? 27.3. I don't have time for that 0.3. Okay, so I'm just going to call it 27. But I know that I'm overestimating this by 20%. You got me? So this approximately is 27. Well, 27 times 1.3. 30 and some change, 33 maybe, but it's not. It's going to be really high. So you could take what's 30%? So 0.3. So what's 30% of 27? 9. So that's going to be what? So 27 plus 9 is what? 36. And so you know that this is overestimated. This is high. So we're looking for something in the 30 to 35 range. What's well, not even that. We're looking for something that's lower than 36. Well, who's that? B weighs 28 grams per mole, right? Everything else weighs way more than that. And then A is way too small. It's only 14 grams per mole. So the only one that made was close to our estimation was B. Question.
I think this is the 22.4 conversion factor and it works out. Is it like a bad thing?
You don't have STP conditions. You got lucky by chance. Okay. Let's not get lucky. Let's be right. Okay. 4. You had to set up a what here? I'm trying not to spend more than like 30 seconds question. What do you have to set up here? Limiting reagent question, right? So you have your little N2, you get your two O2s yielding dinitrogen tetroxide. You can set up a BDA table with pressures at the same temperatures and volume, okay? So you can set up just like you would with moles, because moles and pressure are directly related, set up with pressure. So what was the pressure of nitrogen? 1 atmosphere. What was the pressure of oxygen? 1.5. Who's your LR? Oxygen, because 1.5 divided by 2 is 0.75. That's more, so this was your LR. Who are you subtracting? All the 1.5, right, this one's gone. What are you subtracting over here? 1.5 divided by 2, because it's 1 to 2 ratio, or 2 to ratio. And then it said, assuming the partial pressure of nitrogen or dinitrogen tetroxide was 0.75, right? Right, so you know you have 0 of this left. How much of this do you have left? 0.25. So 1 minus 0.75 is 0.25. So then what's our total pressure? 1. Easy math, not easy setup necessarily, but easy math. So that should be C. Number 4, what was your decomposition reaction? 5. CaCO3 yields calcium oxide and carbon dioxide. Okay, all on a 1:1:1 ratio, which makes it nice. What do we start with? Moles of what? Calcium carbonate, which exists in a ratio of 1:1. What are we going to though? CO2, right? Because we have to deal with a gas, and that's the biggest problem. Most people forget that we're dealing with gases, so they'll just kind of go with the flow and put moles of whatever in there. So we are going to moles of gas. Well, that's the same thing, 0.33. So then what are we plugging this into? Ideal gas law, right? So what are we solving for in the ideal gas law? Pressure. So pressure is equal to nRT over V. So N 0.33 moles times 0.0821 atmosphere liters per mole K times 300. Yeah. 300 Kelvin, and what was the volume? 1 liter. Okay. You estimate for me. What are you starting with? So, say again? Okay, so you're going to take 0.33 times 300. What is that? Approximately 100, right? Well, it should be really close to 100. And then on 100 times what? So what is that? 8 and some change? The only answer is 8.9. Okay, pretty easy math on that one. 6, I think you guys can see now. Actually, let me ask you. How do you guys feel about 6? Okay, why is 2, like II, not right? Alright, it's not the lightest, right? What's more mass of nitrogen? 28 grams per mole, where ammonia is actually 17 grams per mole. It's the lightest. And they're all not going to fuse at the same rate because what do we know about effusion? So rate of effusion is related to velocity. Velocity is related to mass, right? Mass and velocity are inversely related. And as carbon dioxide, which weighs what? 44 grams per mole, it's not going to effuse as fast, so overall it's going to stay in the balloon, therefore its mass will increase, meaning its moles will increase, meaning its mole fraction will increase. All right, number 7. We're like not 120. Okay, number 7, what law came to mind? Law. P1 over T1 equals P2 over T2. What were you solving for? P2, so P2 is equal to P1 times T2 over, thank you, Cassie, over what? T1. You should probably be writing this stuff down, because if not, you're going to accidentally plug something in the wrong place. Hi. Bye. Okay. All right, so what's our pressure 1? What's our pressure 1? 0.5 atmospheres. What's our T2? 400 Kelvin. What's our T1? So you're basically doing 0.5 times 2, which is 0.5 times, this is 2, which is 1. Okay? So try to simplify your math as much as you can. 8, what did you have to do? You had to do what? Basically to the Celsius, add 273, but in the end we subtracted because it was a negative 196. So you take your Celsius plus 273 to get to Kelvin. Okay, and that's 77 Kelvin. 1.1 atmosphere, sorry, not atmosphere, yeah, 1.1 atmosphere is going to be a little bit greater than 760 mils of mercury, so the only answer there was A. I'm sorry about the units not being there, but A was millimeters of mercury. 10, you guys know the inverse relationship. 11, give me like a thumbs up right here on your chest or a thumbs down if you have it right. Just on your chest. I want the whole world to know. Okay, so the idea is that you are looking to see which variables allow for a gas to approach ideal behavior. What are some characteristics of ideal behavior? No, characteristics of ideal behavior. Okay, elastic collisions, what else? No volume, and do they interact? No. Okay, so basically what are the conditions that are going to stop them from interacting? Okay, a lot of space to play, which is low pressure conditions, and flying past each other with no regard for the other particles, meaning they're moving fast, which means high temperature. 12, this is the definition. 0 Kelvin is as low as we can go, which is negative 273 Celsius. That's 0 Kelvin is absolute 0. 13, where it said absolute temperature, did you guys realize that meant Kelvin? Some of you guys maybe did. So that might have been a weird word, but absolute temperature means Kelvin temperature, because that's our absolute temperature scale that we work with in chemistry. All right, so for 13, how did you guys approach that? You did algebra. Okay, so what did you do?
1.0 liters times 1 over 1.
Times whatever what?
Times 1 over 1. So like dV over 2.
Okay.
Is equal to 1/3.
Oh, okay. It's equal to 1/3. So 4 liters times 1 over 1 is equal to 1/3 times divided by 1/2. Multiply by what? Volume. Okay. So essentially, this right here makes what? So the 2 comes to the top, right? So, well, why is it 2/3? It is 2/3, but that's not going to give the right. Oh, no, but you're going to the other side. Okay, good. So this is 2/3. So then how did you modify and get V? So 4 times 3 is 12, divided by 2 is 6. Okay, so you could set up like combined gas law, which is, it looks like what you did to us, P1 V1 over T1 equals P2 V2 over T2, and solve with these fractions. Or think about it conceptually. If you have 4 liters, okay, and you decrease the pressure to 1/3, how are pressure and volume related? Direct or indirect? Be confident, people. Indirect. Okay, so you have your volume, you decrease the pressure by 1/3. What happens to your volume? It increases by 3. So 4 went to 12. It's all multiplication, right? So now we have a 12-liter container. But then the temperature is decreased by half. How are temperature and volume related? directly. So if our volume is 12 and then we decrease temperature to half, then our volume also halves. So I didn't do the math, I just did the log, which might save you some time. 14. So what did you guys do to your Celsius on 14? You did what? Converted to Kelvin. Most people would just go, oh, 100 to 300 is a 3 times increase, which is not the case for gases. We have to convert these to Kelvin. Kelvin is not related to Celsius in a proportional manner. It's an addition. So proportional means like division and multiplication. So this is, what's this in Kelvin? 373 Kelvin, and this is 573. Are these, what's the multiple here? Less than even 2, certainly less than 3. So if that's less than twice the temperature, then the pressure is not going to increase by twice, not even twice, certainly not 3. So it's going to be increased by a factor less than 3C. 15, what gas law came to mind? Combined gas law, P1 V1 over T1 is equal to P2 V2 over T2. So when you have this, what were you solving for here? Volume what? Volume 2. So what's V2 equivalent to in terms of variables? P1 V1 T2. So you're multiplying across here over P2 times T1. Okay, so all you had to do was look at the variables, plug the right one in the right place, matched up with the math that was there. They didn't give you any units, but they're all the same units. They will cancel out. And then 16, what gas law came to mind? Graham's law, which is the one with velocity. So what did you set up? So rate of what over rate of what? Who went on top? Well, in the rate, you set up one way, but in your oh, you guys put CH4 first. Okay. Notice how this is phrased. The ratio of SO2 to methane. So the way this is phrased in the answer choices, do you see that there's inverses of each other? 1 and 4, 4 and 1, 1 and 2, 2 and 1. You have to go in the order they suggested here. So the rate of SO2 versus CH4, and then in your ratio, or in your square root here, that's when you invert. So what goes on top here? 16 grams per mole, and on bottom? 64 grams per mole. I know this is math, but if you simplify this, 1/4, right? So 16 over 64 is 1/4. What's the square root of 1? 1. What's the square root of 4? 2. So the ratio is 1 to 2. Yeah.
That's for average velocity, so why can we use the equation?
So the average velocity, so this all relates back to the kinetic energy is equal to 3RT over molar mass. So because the average velocity is related to the Kelvin temperature, we pulled this out of the equation because when we stack this fraction and this fraction, the only numbers that stay with us are the molar masses. So, but it's because it relates back to the kinetic electrotheory definition. Okay? All right. And stand up and take a break for a second. Talk to somebody about gases if you've been speaking on me. It's kind of a review day, and tomorrow's review day, so I talk more than needed on reviews. Maybe talk about that redox in real life poster that's due Monday. Okay? Unfortunately, it's due Monday in intervention because we are presenting during intervention. Make plans. All right, guys, come back to me. Come back to me. Okay, so I'm going to try to check FRQs for like 15 minutes and that's it. Now, other questions from FRQs I'll answer more later. So, just a quick thought. Who remembers this from Honors County? Phase diagrams? Okay, some of you guys had teachers who left you in like November, so I was like the scary person that came in and helped. But this is just something to be familiar with because we're kind of in our unit of gases. What you're looking at here is a phase diagram. What are the three phases of matter? Solid, liquid, gas. And so as you can probably imagine, under really high pressures and low temperatures, which state of matter do you think would exist if it hadn't condensed? Potentially solid. Look at the graph here. At high, water's weird. Water's an anomaly. Let me go with CO2. So high pressures, which you can see CO2, which normally does exist as a gas at room temperature. I'm sorry, normal atmospheric conditions. Down here, 1 atmosphere. All these are really high pressures. Yet again, though, high pressure, and then the temperature scale being on the x-axis down here, low temperatures. You're going to be in the solid region. Okay. Now, what's the phase change called when you go from solid to liquid? Melting. So solid to liquid is melting, and then if you went from, this is going to expand up some, as you go from liquid to the gaseous region, it's called vaporization. What's the reverse of vaporization? Condensation. What's the reverse of liquid to solid? I mean, what is liquid to solid? Freezing. And what's solid directly to gas? Sublimation and reverse. What's the D? Deposition, right? So there's just some terminology here. I'm like 99.99% sure I have nothing like this on multiple choice, but I have to introduce you to the phase diagram, so we'll use them more in our next unit. But the idea is that it's always in the same order: solid, liquid, gas, because the relationships how pressure and temperature condense matter. And then we understand that every single compound type or element has their own specific phase diagram. Like this is for water, and this is for carbon dioxide, so we can read information that we already know about water. When does water melt at 1 atmosphere? 0 degrees Celsius, right? So what we should see from, here's our 1 atmosphere. As you go across the border from solid to liquid, that's happening at right there, which is approximately what? 0 Celsius, right? And when does water at this still 1 atmosphere condition, when does water boil? At 100 degrees Celsius, right there. So you can actually determine melting points and boiling points and freezing points and so forth from a graph. Okay, we'll go over this more later. Ready for FRQs? Okay, have your same colorful device to kind of, I'll try to document point values as we go. I make up some of them, but I have a pretty good idea of what point values fall, where they fall. All right, so I have done these FRQs about 17 times. So I've got like a million answer keys, but I tried to dumb them down to just the stuff that you would need to write. Notice that I'm okay with abbreviations for our class, like P is pressure, T is temperature, V is volume. On your AP exam, you have to spell some things out. So we got some package, but for simplicity and abbreviation sakes, I'm fine. As long as it's like normal abbreviation. If you like abbreviate H for something, I'm not going to know what you mean. I'm going to think hydrogen if you're trying to say like, I don't know, something else, I don't know. So don't choose crazy abbreviations. All right, so in the first one, it had those scenarios where you had to explain it according to the KMT. I have my FRQs up here. So, when a gas balloon is cooled and it shrinks in volume, this occurs because no matter what gas is placed, or this occurs no matter what gas is placed in the balloon. What two variables are we speaking to? Temperature and volume, so they are directly related. Okay, so I said as you decrease the temperature, the volume decreases because of lower velocities, which causes less collisions with the container walls, hence a lower pressure. So to keep the pressure constant, we must decrease the volume to keep the collisions constant, consistent with the container wall. So it's relating temperature to volume, to velocities, and then keeping your pressure constant. You need to shrink the volume so they're still with the same number of collisions. Something like that, okay? I also have a paragraph I could read, but I'm not going to paragraph. B, when the balloon is described in A is cooled further, the volume does not become 0, rather it becomes a liquid or solid. So technically here, matter cannot be destroyed, so we can't have 0 volume. All matter takes up space. That's kind of like the background knowledge. But as things start to cool down, like I just showed you on the phase diagram, they can condense, meaning they'll go to their what phase? Liquid phase, right? Or technically they could go to their solid phase. So as they start to move more slowly, they can then interact through IMFs. What's IMFs mean? Intermolecular forces, and once those intermolecular forces come into play, they can then condense into a different state of matter. Something like that. Okay? C, when ammonia gas is introduced at one end of the long tube, simultaneously HCl is introduced on the other end. A ring of ammonium chloride is formed in the tube. In a few minutes, the ring is closer to HCl than the ammonia. This is two gases are traveling. So if they're traveling, we're talking about a fusion. So what should you be considering? Something about molar mass. Was HCl's molar mass? Approximately 36-ish grams per mole. So ammonia moves quicker, meaning it has a higher rate of fusion or a higher velocity because its molar mass is 17 grams per mole versus HCl, which is about 36 grams per mole. So it travels a greater distance in that same amount of time, right? It's always its rate of diffusion per time, just like it travels 4 miles per hour. They usually describe this as meters per second, but we weren't asked to calculate that. So if you just say velocity or rate of diffusion, you're good there. Can I move on? Give me some emotional feedback. Okay. And D, I whittled it down to like 3 words, but the question said, flag waves in the wind. Some of you guys are like, what does this even mean? But the flag waves in the wind, you have unidirectional wind, right? So wind is moving in one direction. It is a gas, and it transfers its energy through collisions to the flag, which is why it waves. So I kind of just put transfer of energy in collisions, but it's really the gas particles in the wind that are doing that. So they like to give you real life scenarios sometimes. Other than that, you could put unidirectional collisions. All right, moving on. 2. And I have to do this one from here. If you do want to see non-long-winded responses, I will upload my key later, but they're too long. They're too long for the time you have. So that's why I try to whittle them down. So 2 felt good about 2. Some of us, okay. There was a point where you had to get to the molecular mass, or the elemental mass of Q may have been the challenging part. So first part, you plug in molar mass is equal to derivative of P. You have everything you need to do that. So your molecular weight of X, which X, Y, and Z all are just compounds with Q embedded as an atom in them. You got 88.1 grams per mole. You got a point for my point guys in here. You got a point. You got 2 points for this question. 1 point for plugging in your work with units. 1 point for, 1 point for your molar mass being correct. Yes, ma'am. Yeah, so ideal gas law or this worked the same way, because in this one you would have assumed 1 liter, and you would have converted. Actually, how did you get moles? Oh, you found your own moles and then divided. Okay. Regardless, your work with units is 1 point. Your final answer is 1 point. So then in B, it asked to find the quantity that Q made up the mass of in X, Y, and Z. So you were given percentages. So as long as you take your percent of Q, which is just the percent by mass of Q, and multiply that by the molar masses of X, Y, and Z, you get the grams that Q makes up in each of those compounds X, Y, and Z. So 57 grams, it's not per mole. I haven't changed my answer key since I scanned this in like 2013. It's not per mole, it's just grams of Q, 75.92 grams, and then 37.95 grams. That should be all to 3 cigs, truly. So 57.1, 95.9, or 90, 57.9, and then 38.0. Okay, and then you got 1 point for each of those, so that's 3 points for that question D. Try to put like +1 where you're getting your points, because then it helps you focus on what you're getting points for, and then like the frivolous stuff you're writing about, like your dog or drawing pictures, then it's not going to help you get points. Okay, and so the next part was the part where I think some people struggled. You had to find the atomic weight of Q. So since we know that Q exists in these masses as whole number atoms or whole number ratios, it's like you're finding the greatest common factor, what's going into each of those masses a whole integer number of times. So the only way to really do that without just sitting and thinking what number goes into all these numbers and sitting and just trying to calculate in your head is you find the ratios of those masses with themselves. So it's like the empirical formula where we take the number of moles and divide it by the lowest number of moles, but we're doing this with grams instead. So the 37 divided by itself gives us 1. The 76 1 divided by the 38 0.81 gives us 2, and then the 57.99 divided by 37.95 gives us 1.5. So I have these numbers here first. 1, 2, and 1.5. So this is supposed to represent the number of Q atoms in these compounds. I can't have 1.5 atoms of Q. So I have to find a way to get that to a full integer. So if I multiply this by 2, it gets me to 3. So I have 3 atoms or 3 molar quantities of Q. I must then multiply this one and this one by 2 because it need to stay in the same ratio. So then I had 4 moles of Q in, I think this was X, or maybe this was Y. Y, this is Z, okay, I'm in order. No, this is X, right? And this is Z, yeah. And then in mole, or in Z, I had 2 moles. So that gets you to the point where you're like, okay, now what do I do? Now I know the molar quantities, but I still don't know the molar mass of Q in each sample. So what you can do is you set up an equivalency. And this was my example here. You could choose any of them, but this one works best. So 2 moles of Q is equal to this mass. So 2 moles of Q is equal to the 38 grams that we had figured out in part B. So if that's equivalent, then you can whittle that down to just 1 mole. And so 1 mole of Q weighs 19 grams, which that is its molar mass. So technically, who is Q? Fluorine. They didn't ask for that, but you could figure that out if it was asked to be. Yes? Since the ratio is the same for all of them, just take the simplest one and find the individual Q mass. They'll work out the same for all of them. All right, and the next one was actually combustion analysis. Did anybody recognize that? Okay, so things start to be more cumulative as we learn more. It's a curse, but it does. So as you take your combustion analysis, your CO2 and your water to moles of carbon and hydrogen separately, and then to grams of carbon and hydrogen separately, you can compare that to the mass of Z given, which was 1 gram. So 1 gram of Z, subtract your grams of carbon, which was 0.37, and your grams of hydrogen, which was 0.0312 grams. That gives you a little teeny bit of Q left, which was in your problem. And that Q mass was 0.595 grams. Then you can take that and figure out, according to the molar mass you have in C, because it is cumulative, so you need to consider part C to find, or part B to find part C and D. You get your Q moles to be 0.0313 moles. And then, like empirical formula always goes, look at all your moles, divide by your lowest one, and you get your quantities be a 1-to-1-to-1 ratio, because this is 0.03, this is 0.03, and this is 0.03, so when you divide, it's a 1-to-1-to-1. And then, once you take your 1-to-1-to-1 and add up your carbon, hydrogen, and Q, which we know is 19 grams per mole, you get your empirical formula mass to be 32 grams per mole. And then the question also gave you, in the table from part A, the molar mass of Z was 64 grams per mole. So that ratio is a 2-to-1. So your molecular formula would be twice as big as the empirical formula, which would be C2H2Q2. Big problem. Big problem. All right, so I didn't tell you the point values for C. For C, showing the mathematical reasoning from like taking grams divided by grams and then concluding with 19 grams per mole, those were worth 2 points. So the mathematical background on C, and then finding 19 grams per mole is 1 point. And then on D, this one, you got 4 points. 1 point for getting to moles. 1 point for getting to moles of your carbon and hydrogen, not each one, but like 1 point total. You got 1 point total for getting to Q moles. You got 1 point for getting to the EF, empirical formula mass. And you got 1 point for getting to the molecular formula itself. Okay? You guys doing okay? I know you're sleepy, but I could just put this up online, but I'm not sure if it will help you 100%. Okay? Looking at 3. We'll do a stretch break again in a second. 3, who felt better about 3 than 2? Most of us overall felt better with this one. Okay. So I'm just checking your answers in your work right now. And I'm videoing, and I'll put the answer key up later. That's about all I can do. So in terms of the hydrogen gas and the water vapor, you just have to take those into account separately. So the total pressure is equal to partial pressure of water vapor and gas. So I just saw for partial pressure of gas first to be 72.1 or 721.2 millimeters of mercury. plugging that into the ideal gas law, solving for n, I usually just rearrange first, just to make sure I'm good with putting my numbers in. And then I sometimes will show my work inherently in the problem, and you guys can do that. You'll get all your points, no worries, as long as you show your units, by the way. So that should give you 0.00349 moles of hydrogen. Thumbs up if I can move on. You've probably got, you got 2 points for that question. 1 point for isolating the partial pressure of said gas, and then 1 point for plugging in and getting the correct answer for moles of hydrogen. And how many sig figs should we have? Was it 90 or was it 90.0? 90.0? 90.0, so 3 sig figs. So we're good here. Back in the day when they had this question, it was a sig fig question. Like I said, on the AP exam, there was only one question they grade for like accuracy for sig figs, but we don't know which it is, so we can do it on all of them. Okay, they're not like, hey, this is the sig fig question. Okay. B, you do the same story, but with water vapor pressure. So the water vapor pressure they gave you is 23.8, blah, 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 all the same. You get your water vapor to be 0.000115 moles of hydrogen, water. So that one you got 2 points. 1 point for plugging in the correct water vapor pressure, and then converting to atmospheres if that's what you're doing here, and then 1 point for the moles here. Yeah.
What is the range of double values?
Excuse me? Oh, it's as long as it's a 3 sig figs, it's probably like a plus or minus 0.5 or 5%. They sometimes give us ranges like on our answer keys, but then this one, what'd you put?
I put 0.0000694.
694?
Yeah, I got 6.94 times 2. Oh, just kidding.
Just kidding. Is he good?
Oh yeah, I found molecules. Okay, yeah.
Oh yeah, so we're almost there. I was like, I don't know how you would have gotten that. Oh, I lied. That was not the 2 points. I'm looking at now the molecule side. So this was understood that you could do the partial pressure here. So you got 1 point for moles of hydrogen, and then taking the number of moles you got, even if the number of moles you got were wrong, you got a point for proceeding using Avogadro's numbers to molecules. So if the way you did this one is equivalent to the 6.94 times 10 19th molecules, you got 1 point here and 1 point here. But if you got your moles wrong, but you followed through correctly, you still get your second point. Question?
If you didn't even get some moles and you just know that there was no moles and you use Avogadro's,
You would get your second point. Yeah, so try not, if you get stuck on something, come up with some creative, weird problem solving. They're like, man, this person's creative. They got it wrong, but they're creative, and they try to proceed, okay? All right, rate ratio, hydrogen gas on water. Hydrogen gas goes on top, because it's what? Lighter. Invert the molar masses, 18 over 2, square root of 9 is what? 3, you did not need a calculator for that. But hydrogen gas moves 3 times faster than water molecules. And between the two gases here, you have water vapor, which is H2O, versus hydrogen gas. What do we know about hydrogen gas in terms of polarity? I know this is background. Polar or nonpolar? Nonpolar because it's H bonded to H. It's an equivalent structure. It's symmetrical. There's no poles, meaning there's no opposite ends in terms of where electrons exist. So this is nonpolar. Water, you guys might remember, looks like this. It's bent. Okay, so is there an unequal or equal distribution of electrons? Unequal. So is it polar or nonpolar? Polar. So we already probably knew that from like, I don't know, 6th grade. Water is polar. So if you're talking about the IMFs here in part D, you have intermolecular forces at play with polar molecules that are much stronger than the intermolecular forces present between nonpolar molecules. So if two molecules interact strongly, they're going to deviate from ideal gas behavior. Because we say in ideal gases they don't interact. So as soon as they start interacting, they're going to do what with pressure? So two particles independently will collide like crazy with the container wall. Two particles that are attracted will lessen collisions, which would therefore lessen pressure or lower pressure. And they technically, as they condense, they take up more volume, they take up more space. So as that occurs, it's going to decrease the volume overall that they could play in, that they could move around in, which would deviate from ideal gas behavior as well. Yeah. So hydrogen would act more like an ideal gas. Water would act less like an ideal gas, more like a real gas. So overall, I just said water deviates from ideal gas behavior due to its stronger intermolecular forces, due to its polarity. That's probably about, actually, in reference to how you answer questions, if they give you two quantities or two identities or two things to compare, comparing one is not enough. You have to mention both of them in your response. So note to self, some of you guys on your redox test need to, I can't give you that back yet, but soon enough, you'll notice that you must mention both quantities. So water is going to deviate because polar. You compare that to the weaker interactions that a non-polar hydrogen molecule would have. So you must mention both. Okay. All right. 4. You guys want me to do 4 or 5 first? Because I'm going to run out of time. 5. Do I have that one here? Hold on. I've cleaned up some of my keys. Oh, yeah, this one's good. Okay. Alright, so this one's on the back of a paper. It's hard to see because I was doing it on the couch last night. Trying to simplify my work. I was a young, dumb AP Chem teacher, and then I've smartened up, so I've simplified my work. So in this case, you had equimolar hydrogen gas and oxygen gas and like 2 milliliters of water vapor. They gave you volume, temperature, and pressure, total, and then water vapor pressure. It said first, what did it say first? Solve for what? Reactants remaining after the reaction. So as soon as you hear after the reaction, what do you guys think you probably have set up? A VDA table, likely. Okay, and then it says calculate the number of moles of reactant remaining, so that means that one of them is the limiting reagent, okay? So the way I felt it was most appropriate to attempt this was to plug this information in by first isolating the 2 individual gases. So the partial pressure of water vapor need to be subtracted from the total pressure. So when I subtracted and I got individual pressures, excuse me, I got the hydrogen and the oxygen collective pressure. It was 1122 millimeters of mercury. And then I went ahead and converted that to atmospheres because I knew eventually I was going to have to use the ideal gas law. So that's collective H2 gas and O2 gas is 1.476 atmospheres. You with me? Okay. It was equimolar, right? So if they both have the same number of moles, that means their mole fraction is what? So what's their mole fraction? No, their mole fraction is not 1 to 1. Their mole ratio is 1 to 1. 1 over 2, right? So 1 mole of hydrogen gas over the 2 moles total. Regardless, if I did 15 moles of hydrogen gas and I have 30 total, it's still 1/2. So the mole fraction is 1/2. So their pressures are the same, but it's half of the total pressure. So their total pressure would be, this is me finding moles total, okay? Their total pressure was the atmospheres we just found here, 1.476 atmospheres, equaling finding the total moles present, times by V divided by RT. You get total moles of hydrogen and oxygen collected is 0.030 moles. And I don't know how many sig figs, but we'll go back to that in a second. So if that was the total moles, then half of that would be the amount of hydrogen and the other half would be the amount of oxygen. So I got each of them would be 0.015 moles. 0.015 moles. I saw this like 3 different ways, but this was the simplest. Does this make sense? Total, isolate the hydrogen and oxygen, take your total pressure, find your total moles, notice that it's an equimolar, cut that value in half, you get each of them with equal moles. So then, now that you have moles you can work with, you can plug that into my little small VDA right here, but the ratio is a 2 to 1 for hydrogen to oxygen. So here's your LR. Hydrogen, because you require twice as much of it to react. So as you take that into account, your LR, you subtract all the LR, which doesn't matter. You subtract half of the 0.015 from oxygen, which leaves you with half of it remaining. So that's 0.0075 moles. And so the reactant remaining is oxygen. The amount of that reactant remains 0.0075 moles. Okay? And then it said to find the partial pressure of oxygen. I'm guessing. Is that what it said? Is that what it said? Partial pressure of what? Oh, I just lost my focus. Oh, the total pressure of the container at the conclusion of the reaction. Okay, so the total pressure at the conclusion of the reaction is including the partial pressure of oxygen that's remaining because of this remainder, and then the water vapor that was present with the 2 milliliters because otherwise, even if you make more water, you're not going to necessarily make water gas. You're going to make water liquid, which at this temperature is going to have the same partial pressure that they gave you initially, because they did not tell you, I'm sorry, at the temperature they gave you 90 degrees Celsius, they told you the new partial pressure of water vapor to be 526 mils of mercury. So take your individual oxygen and you're going to add it to the partial pressure of water vapor they gave you to get the P total. So you actually have to get the partial pressure of oxygen first by plugging in the moles you just got, RT over V, and then you get your partial pressure of oxygen in millimeters of mercury to be 358.5 millimeters of mercury, and then you're going to add this to the partial pressure of water they gave you in part B, and then add those together, you get 884 millimeters of mercury. Whew. Okay, and then as there see, calculate the number. Can you guys calculate the number of moles? What do you have to do? I need to scan this one. Ideal gas law, using the partial pressure of water vapor, convert that to atmospheres first, plug them to ideal gas law, solve for N. Okay, we have about 5 minutes left. So how about tomorrow I'll check one more FRQ, book number 4, and maybe number 6. So what I'd like for you to do is practice where you need it, but here's what my expectation is, okay? I have given you, I'll look on the back of the multiple choice I gave you. Actually, you guys need more multiple choice practice. Okay, so before I move on, go back to your FRQ sheet that I gave you like a couple days ago for Emily's. Do you guys see this right here? There are 17 problems, but they're all from different years, like 1999, 1994, 1995. I want you to just sit down for 20 minutes and go through this in your calculator. Okay? And that will give me a chance to just check those with you tomorrow versus give you time in class because we'll have a shortened class period. So do all the multiple choice that are on here with no calculator. Don't ask anybody. Let's just do what you can do personally. Try to do your little cheap mental math tricks without any help. And 1 second. You'll do another FRQ tomorrow in class. We'll check on multiple choice. And I just said beginning review. I'll ask for some of your year review as study evidence from today. Because I think you guys notice it's now up to you to figure out what you need to practice. If it's multiple choice you practice, I'll try to find some more experience wants you to practice. I'd rather have you for more. There's just general review. There's all kinds of great stuff on my website for that. Okay, sweet? So you're right. Let me go back and find my action sheet. As you guys are kind of working through talking in a second, let me tell you which one was it for you? For 19 elastic. Right. So what Kui is saying is on the multiple choice that I'm having you guys do you see number 19 at the end, number 19? Can you guys see the neon and argon numbers? Can you see them? Neon and argon. Neon, it says 0.5 liters and 1.25 atmospheres. And argon, it says 0.20 liters and 1.75 atmospheres. I think that's all you can't see. Right? Say again? Oh, answer choices. So A, B, C, and D. D is 3.0, C is 1.5, B is 1.4, A is 0.5. Sorry about that. That's number 19 at the end. There's like a little diagram with it. I'm just going to try to stay out of this. Alright, so who is not going to be tomorrow? Anybody? Oh, no one. Okay. So just watch the video for us reviewing multiple choice and food. Okay. You're leaving me shortly. Keep thinking about that redox in real life. Digital poster or physical poster. Let me stop this video. Oh, actually, I can flash up 4. We'll do that. Here's number 4 if you want to check anything. Oh, just put it on Margaret's desk.
Yes.
Oh, it's actually gonna be really fun. That's what it was answer. Do you know when Chase will be taking his test? Do I have to cover it with they're like overlapping a bit? So like this. I got it.
Here's number 4 if you want. I'm just gonna keep it up here on the board. There you go. I have like him. That was a horrible spiral through, CJ. Alright, and then you get my text.
I thought exactly that's why it's a little fishy, like a little. It's just a little. Yeah, I went up and I said, oh my god, it's just the same thing. Almost. I thought we were going
Guys, another good point. If you want some more multiple choice practice, you know you have that self-assessment in the back of chapter 5 of your textbook, whatever the guys have.
Okay, so do that too.